Okay, I talked a little bit about this in the video on vocabulary for kinematics, but I wanted to talk a little more about the calculus that we use in introductory physics. All right, so let's get started. We're talking about motion, and that involves position, velocity, and acceleration when we talk about how motion is changing. And we're going to look at graphs of each of those. So I'm going to start with a position versus time graph, a velocity versus time graph, and an acceleration versus time graph. All right, so we need to start simple. So let's look at no acceleration. A equals to 0. All right, we defined A to be the time derivative of velocity, which we denote this way, or this way, or this way. Lots of ways we can denote it. So if that's equal to 0, then velocity is not changing. All right, that's something that will arise again and again in our introductory physics examples. If we have a constant velocity, that means that we know our acceleration is 0. All right, so let's just pick an initial velocity. We'll say we have some constant positive velocity v0. What does the position versus time look like? Let's assume that we start at 0 and we're moving at some constant velocity v0. So that means each second we cover some distance based on that speed. And that distance is the same. So each second we move up the same amount. That gives us a linear position graph. All right, how do we arrive at that? We arrived at that in a very mathematical way, but we didn't really use calculus is what I want to talk about, right? We didn't really have to because this is a straightforward graph, right? You learn in middle school that distance is equal to rate times time. All right, so delta x is equal to v times t. And when we relate that to our graph, v times t is the area under the graph. All right, now we're starting to talk about calculus, right? When we take an integral, that gives us the area under a curve. Right, or antiderivative, if you like that language. Right, we know that the derivative of position is velocity, the derivative of velocity is acceleration. So if we take the antiderivative of our velocity graph, then we get the changes in position. Note that you don't know the initial position though. You have to have some unknown. And we talked about that in the previous video where you have the constant of integration, right? All right, so let's look at one where we have a non-zero acceleration. just some a not equal to 0. All right, so now if we were to integrate this over some time t, from say t0 to t1, we would get some area, and that would be the change in velocity. So this time I'm not going to assume that my initial velocity is 0. We're going to assume some unknown v0. And for each second, we have some change in velocity. But that is the same because we have a constant a. So we get a linear velocity graph for our constant acceleration graph. Right, and in the previous video, we talked about this in terms of slopes, right? The slope of this graph is a constant, and that gives us this constant value for acceleration. Now we're working backwards. We're integrating instead of taking derivatives. All right, so now we get to the difficult part, right? How do we get our x graph from our v graph? Well, if we were to look at integrating this, you see that you have two kind of distinct regions in this graph, right? We have this rectangular region and we have this triangular region. And we know how to find the area under the rectangle really easily. But let's see. So if we look at the area under the rectangle, that would denote, or that would give us, again, we'll assume some unknown x0, just the area under the rectangle, which I'm going to do in green. Right, that would be a constant value, and that would give us a linear increase. But that's not everything that's going on, right? We also have all of this area, which is getting bigger, faster, and faster, and faster. So what we actually get is a quadratic, right? When we add that red portion onto that. And that's what we get for our final curve. Is that quadratic? Guess I should have graphed the red by itself. All right, let's look at this mathematically. Let's assume that we have an acceleration of 2 meters per second squared. When we integrate that over some time, I guess that we'll do it in general. We went through this before, so I'm going to go through it quickly. We get that v is v0 plus at. So let's do it in general. Just some a, which is constant. When we integrate again, we get x is x0 plus v0 t plus 1/2 a t squared, just from integrating. Well, for our constant a, we see that this is a linear equation and a quadratic equation. All right, maybe this is beating a dead horse since we've talked about some of this in the previous video, but this is an important concept to understand the relationships of position, velocity, and acceleration. Most people in day-to-day life have a pretty good idea of what position and velocity are, right? you can see those, right? You can see a difference in the location of something, and you can see that something's moving. A is a little harder to conceptualize. That really is the rate of change of the speed. And that's not something you can easily take in with your senses, right? That requires some type of measurement to really quantify that. We'll spend a lot of time with these variables and these kinds of graphs in a lot of situations, and you'll get used to them. This is just things to think about before we get into class.